In this penultimate part of the lecture, I now want to introduce some key concepts associated with the Bayesian paradigm to statistical inference. So far, we've covered concepts, but only from two of the three main paradigms that are commonly used for statistical inference. That is from the likelihood paradigm and the frequentist paradigm. Now, the likelihood paradigm is based, as you know, on the concept that we use repeated sampling to gain inference about theta. So essentially, we're going to assume a model for the process that generated the observed data, a probability distribution, and we're then going to study variation in data samples or sampling distributions that would be attained through hypothetical repetition. So we looked at the distribution of a statistic or an estimate by assuming repeated sampling of size n from the population. Frequentist inference is also based on the idea of repeated sampling, but the focus is on decision problems, so we came across it when we looked at hypothesis testing. And in frequentist inference, the idea is that the optimal inferential procedures we apply should be designed before exposure to the observed data. Now, in both the likelihood and the frequentist inference setting, so in both estimation and hypothesis testing, the variable of interest x was treated as random with a probability distribution that depends on a parameter theta, but theta was treated as a fixed unknown constant that's the target of inference. Well, the Bayesian paradigm takes a very different approach. Under the Bayesian paradigm, both x and theta are treated as random with a joint density, so theta, the parameter, has a distribution. And Bayesian inference draws on Bayes' theorem to make inference about the distribution of theta. And it adopts the viewpoint that while theta has a probability distribution which reflects our uncertainty about it, the thing we do know is the data, small x, and so we should condition on it. So what Bayesian inference does then is it tries to use the data to tell us something about the distribution or the conditional distribution of theta given the data. And it's based on Bayes' theorem, which we covered in lecture 1. I won't repeat it in detail here. If you remember, conditional distributions can be written in this form here, the ratio of the joint to the marginal. And what we said is because there's this symmetry, we can express the joint distribution of E and F, or the joint probability of E and F, in two different ways, involving two different conditional expectations. And so that allows us to turn around conditional probabilities, as in Bayes' theorem. The probability of E given F can be expressed in terms of the probability of F given E, and vice versa. And we said that's important because these two conditional probabilities are not in general the same. And then we showed if for a partition of the sample space, we can use the theorem of total probability to express things in this way. Now, Bayes' theorem holds for events, but it also holds for random variables. So the conditional density of y given x can be written in terms of the conditional density of x given y times the density of y, so that's the joint density of x and y, divided by the marginal density for x. Written here as an integral because if we integrate over this joint density of x and y, if we integrate y out of that joint density, as we know, we're going to end up with the marginal density of x. So it's not a great leap to get from this to this. All we're using is the relationships that we have between conditional, joint, and marginal distributions. But this is quite important because what it's saying is that two random variables can be analysed using Bayes' theorem. And that's the principle of Bayesian inference. In this case, the random variables we're interested in are the parameter theta and the data x. And we're going to look at the conditional density of our parameter theta given the data. And that's expressed, simply as it was in the previous slide, as the ratio of the joint density of theta and x to the marginal density of x, where again this marginal density of x is achieved by integrating over the parameter. So that is a Bayesian inferential calculation, and I want to look at the main elements of it, which are defined here. So first, on the left hand side we have the conditional density of theta given x. This is actually referred to as the posterior distribution of theta given x, and it captures our inference about theta conditional on the data. To calculate this quantity we have to evaluate this ratio. There's three components to it. On the numerator, the first component is the density of theta. This is referred to as the prior distribution. So it's the prior density of theta, and this is intended to capture any beliefs we have about theta before we have seen the data. Next, we have this density here, the conditional density of x given theta. That in this context is in fact a likelihood, and it's a likelihood because we're going to treat that conditional density as a function of theta for fixed x, and thus it's just the likelihood function for theta. Then the final component is the denominator. This is referred to as the marginal likelihood of x, and it does not depend on theta. The purpose of the marginal likelihood, one of the main purposes, is it acts as a normalizing constant which makes the posterior density a proper density in the sense that it will integrate to 1. So the posterior distribution is what we're going to try and estimate. We're going to do it by combining the prior distribution and the likelihood, and we're going to have to evaluate this quantity here, the marginal likelihood. That's often difficult to compute, and there's a technique known as Markov chain Monte Carlo, MCMC, that is used to make that calculation in practice. And it's actually the MCMC, invention of the MCMC algorithms, that really freed up Bayesian inference to be executed in practice. So for Bayesian estimation then, commonly we just write it in this form here. The posterior distribution of x given theta is proportional to the prior times the likelihood. For this proportionality, well, this is true up to a constant of proportionality defined by the marginal likelihood. And once we have the posterior, then Bayesian estimation and inference can be computed. And we don't have time to go into it here, but of course the advantage of the Bayesian approach is that we end up with a distribution of theta which allows for much more flexible inferential procedures to be applied. So for instance, we could look at the posterior expectation, the expected value of theta given x, which is the integral over the parameter space. We could look at the posterior mode, which is the maximization of the posterior with respect to theta. Or we could look at the posterior median that satisfies this quantity here. So it's much more flexible because rather than having a point estimate, we've got a distribution. For interval estimation, again, the fact that we've got a distribution makes matters considerably easier. Again, I won't go into detail about it here, it's not so important. In the Bayesian terminology, interval estimation, we try and estimate what's called credible intervals. So a 100, 1 minus alpha % Bayesian credible interval for theta is some subset C of the parameter space such that the probability of theta falling in C is greater than or equal to 1 minus alpha. You'll also sometimes see talk of higher posterior density credible intervals. Essentially, this is just the shortest interval on a posterior density that we can find for some given confidence level. Okay, and so the first main point really I wanted to make about Bayesian inference is that theta is treated as a variable, and that our inference is conducted on the distribution of theta, the density of theta, given the data. So it's not point estimates, it's for the density. The second main point is that with Bayesian inference, we're able to do what's called sequential learning or Bayesian updating. So suppose we've got some data x1 and we use it to form this posterior. We do it using this expression here. So we form the posterior. Then we obtain further data. So we've conducted our analysis on data x1. Then we obtain further data x2 that's independent of x1. Well, the posterior based on x1 and x2 would be given by this expression here if we analyse them jointly together. That is, the density of theta given x1, x2 is equal to the joint density of x1, x2 and theta over the marginal likelihood. But it turns out that if we write the prior density of theta given x1 in this form here, then the joint density of theta given x1 and x2 can be written in this form here. That is, it can be written as the product of the likelihood of theta given x2 times the posterior of theta given x1 divided by the marginal likelihood. And that's important because what it means is that we don't need actually to analyse the data together. We can use yesterday's posterior as tomorrow's prior, and the resulting posterior we get is the same as if we'd obtained the data together, even though we didn't. So we can update our inference on theta using yesterday's posterior as today's prior when new data becomes available. And that's a very important property of Bayesian inference. If you want to have a look at how these equations work, I've put some algebra here that should show how you can get from this joint density, where things are analysed together, into the one where we've got the likelihood given x2 and the posterior. So these equations there will show you how to do it. I'll give a very quick example of how Bayesian inference works, and that, yeah, I think kind of gives an idea of how Bayesian updating can be used. So in this case, we have a Bernoulli response, and we're going to have a discrete prior. The problem is one that concerns drug efficacy, and we believe that a drug may have a response rate, positive response rate of 0.2, 0.4, 0.6 or 0.8, and each are equal prior probability. So prior to seeing the data, we don't really know which of these response rates is going to be more probable, so we're going to place an equal probability in each of them, a so-called non-informative prior. So the question is, if we observe a single positive response, that is y equals 1 rather than 0, how is our belief going to be revised? Well, we've got our likelihood function in this case that we're going to use is a Bernoulli distribution. Theta is our parameter. It can take 4 different values. The prior distribution we place is uniform. All of these 4 are equally likely at 0.25. We multiply the likelihood by the prior, and it gives us this expression here. We use our marginal likelihood to get the posterior, and this gives us the posterior distribution over here. So that's how the Bayesian calculation would work in this very, very simple case. And what did we learn? Well, before we saw the data, our prior distribution was 0.25 across the board, so it was uniform. But having seen a single positive response, y equals 1, it then makes it 4 times more likely that the response rate is 80% rather than 20%. So the posterior distribution, having conditioned on observed data, updates our prior belief about theta. That's the way Bayesian inference works. And then if we were to obtain further data in the future, independent of the data we already had, this posterior here could be used as the prior in the future calculations, and that would give us inference as if we had jointly conditioned on our original data and the new data that came to hand.